Welcome to the next video in the Measure Theoretic Probability series. In this video, we will pick up where the previous one left off and discuss Vitali's proof of the impossibility of measuring all real numbers. The proof will be by contradiction, so we start by assuming that some measure exists. We call it M, and notice that it has domain, the power set of real numbers. This makes sense because we want to associate to any subset of real numbers its measure. Notice also that its range is the extended real numbers. This means the real numbers together with infinity and negative infinity. The reason for this is that certain subsets of real numbers intuitively should have infinite measure. For instance, the entire real line should have infinite measure, and so should any infinite ray. By infinite ray, I mean an interval like the one with left endpoint 0 and right endpoint infinity, since it starts at a point and goes to infinity. Before moving on to the proof, I want to comment that I will not make entirely precise what properties this function m has. I will do that later, but at least for now, I just want to make some steps which seem like intuitively they should work. Later on, we'll think about exactly what these steps were in a mathematically rigorous formulation and use that to decide how to deal with Vitali's impossibility result. Now, to begin with on this slide, I'm just going to define a bunch of objects. On the next slide, we will make inferences about them to derive a contradiction. Before doing that, I want to just give a bit of intuition about the nature of these objects and how they will be used. First of all, we are going to use the interval from 0 to 1 in order to construct some other object. I will call these other objects feathers, but they will be sets of real numbers. Then I will define another object called V, which will be the union over all of the feathers. Now, why do I call these sets feathers? I do so because if you depict them on the real line by making dashes where the elements are, you would draw a dense but gappy bunch of dashes, kind of like a feather. Anyway, the set V will be the source of the contradiction. We will show that V must have a measure between 1 and 3, but after that, we will show that V must have a measure 0 or infinity, hence a contradiction. That is the summary of the proof. Let's now say a little bit about what the feathers are. We start by constructing a single particular feather by first defining an equivalence relation. Let's not worry too much about the exact nature of that equivalence relation right now. But the important point is that the equivalence relation induces a partition on the interval from 0 to 1. The feather is defined as any complete set of representatives of distinct cells of the partition. Now, that last sentence is probably somewhat hard to parse, but it's important. So take a minute to try to understand it. You can almost think of it like this. Let's have this partition, and there are a bunch of cells of the partition. We take the first one and draw from it any representative element. We take the second and draw from it any representative. We proceed likewise until the end of infinity, so to speak. And of course, I'd say that with really heavy emphasis on the quote unquote, so to speak. But if you then take all of the elements that we drew from this process and assemble them into the set F, then that is our set F. Next, we define all of the other feathers as translations of the feather F. To do so, we start with an enumeration of the rational numbers in the interval from -1 to 1. We call this enumeration R1, R2, and so on. So the other feathers are just F translated by any one of these rational numbers. That is to say, F plus Rn is another feather for each choice of n. Finally, we take the union over all of the feathers to construct v. Let's now say a few words about why the measure of v will be problematic, starting with how we know that v must have measure between 1 and 3. The short answer is that we will prove that v contains the interval from 0 to 1 and therefore has measure at least 1. After all, the interval from 0 to 1 has measure 1. So if v contains that, it should have at least as big a measure. Also, we will show that v is a subset of the interval from -1 to 2. Therefore, by similar reasoning, v has measure at most 3. Of course, I am skipping all of the details and explanation of why these subset relations hold, because I will discuss that in the next slide. But one more thing before we finally do that. Let's say why the measure of v must be either 0 or infinity. First, note that each of the feathers must have the same measure. After all, they are just translated copies of f, and translation should not change the measure of a subset. Therefore, we may call the measure of any feather the constant phi. We will eventually show that the feathers are disjoint from each other. Therefore, in order to measure their disjoint union, it should be the same as summing the individual measures. To take a simple example of this, think of the interval from 5 to 7 and then the interval from 8 to 10. The measure of their union should just be 4 because that's the measure of the first interval plus the measure of the second one. If they were not disjoint, we couldn't quite do that, but disjointness guarantees that we can merely sum the parts. Therefore, since we will show that the feathers are disjoint from each other, we should be able to measure v by summing the measures of each individual feather. But then that's an infinite sum of the constant number c. If c is 0, then the sum is 0. If c is positive, then the sum is infinity. Okay, with all of that outlining done, let's finally move on to the proof. So now let us formally define all of the things that you see here on the slide. The equivalence relation basically just says that any two elements are equivalent if they are a rational distance apart. Notice that all rational numbers in the interval from 0 to 1 are equivalent, according to this equivalence relation. It should be simple enough to prove that this is an equivalence relation, i.e. that it is reflexive, symmetric, and transitive. Therefore, I leave this as an exercise. I've already talked out the details of the rest of the definitions on this slide, so let's move. First, we show that the measure of v is between 1 and 3. To do so, we start with the first inequality, and for this, we will show that the interval from 0 to 1 is a subset of v. Now, to prove this subset relation, we perform a pretty standard element chasing argument. We let x be an element of the interval from 0 to 1 and try to show that x is an element of v. Since we assume that x is in 0 to 1, then since the equivalence relation partitions the interval, we must have x is in some cell of the partition. Since every cell of the partition has a representative in F, then we must have a lambda in F, which is equivalent to x. I now claim that x equals lambda plus r sub n for some n. Prove this, it is enough to show that x equals lambda plus a rational number that is between -1 and 1. Recall that the enumeration is the enumeration of rationals between -1 and 1. So let's start by showing that x equals lambda plus some rational number. Of course, because they are equivalent to each other, they are a rational distance apart. Immediate from this, we know that the needed rational number exists. Next, let's confirm that the rational number is between -1 and 1. This follows from the fact that both x and lambda are in the interval from 0 to 1, and therefore the least that their difference could be is -1. Also, the greatest their difference could be is 1, so we have everything that we need. Now that we know that x is lambda plus Rn, then notice that lambda plus Rn is one of the feathers in the union that defines V. Therefore, this is in V. But that just shows that x is in V, which is what we wanted. Okay, now we can move on to showing that the measure of V is at most 3. Similar to the first part, we showed that V is a subset of the interval from -1 to 2 by an element chasing argument. Let x in V, then x is in one of the feathers, but that means x is lambda plus Rn, with lambda between 0 and 1, and Rn between -1 and 1. Therefore, x is between -1 and 2, whence the claim. So there we have it. The measure of V is between 1 and 3. Next, we show that it is also either 0 or infinity. Most of this part of the argument is exactly what I already talked out earlier and will be in the slide here. The main thing that needs justification still is the claim that the feathers are disjoint. One way of proving that a collection of sets is disjoint is to show that if they have any intersection, then they are the same set. If this is confusing, start by thinking about the more natural way to think about a disjoint collection of sets. If you take any two distinct sets, then they have no intersection. Now take the contrapositive of that state. If two sets have intersection, then they are not distinct, which means they are equal. Okay, so that's going to be our strategy. We assume that there is some element in the intersection of two feathers and show that the two feathers must be equal. To get started, we let x be in the intersection. By definition of the first feather, x is lambda plus Rn. By definition of the second feather, x is lambda plus Rm. Now use transitivity of equality. If we then do a natural move, which is to put the lambdas together on one side and the r's together on the other side, then we see that the lambdas are a rational difference. Since they're in the interval from 0 to 1, then they must be equivalent. But recall that F contains only one representative per cell of the partition. This was the whole blurb about having representatives of distinct partitions. Well, since these two lambdas are in the same cell of the partition, but F has only one lambda per cell of the partition, then the two lambdas must actually be equal to each other. From this, it quickly follows from the previous equations that the r's are equal. From that, it follows that the feathers are equal as desired. Now that we know the feathers are disjoint, we can therefore say that the measure of V is the sum of the individual measures. Therefore, it is the sum over the constant C. Therefore, the measure of V is 0 or infinity, depending on whether C is 0 or positive.